I see the participants coming in.
Yeah, and I think I saw a couple of the previous recordings, like this entire thing gets posted. So like in the previous recordings, there's just like two people silent for like 20,
Just chatting with
30
each other.
seconds or so. Yeah, exactly. It's this babble, beginning babble. So,
well, welcome to everyone who's just starting to join in. Looks like folks are starting to stream in the door. We usually give it a couple minutes just to settle out and let everyone join in. Just a minute or two past the hour, so we'll wait just a little bit longer. All right, Kevin, are you about ready? It looks like we're starting to equilibrate here a little bit in terms of folks coming in. So I'll just give a welcome good day or good morning, good evening, everyone. My name is Danny Park, so I have the privilege of moderating today's session. And today we have the pleasure of having Mr. Kevin Libuit present this webinar. So just a little bit of the ground rules. Kevin will spend the next, I don't know, half hour, 40 minutes or so, just going through some slides and giving his presentation. And during that time, anyone's welcome to kind of type their questions in. You can use the chat. There's also a Q&A feature in the webinar. So feel free to use those, and we'll collect those throughout the course of his presentation. And at the end, last 20 minutes or so, I'll read them out for everyone and give Kevin a chance to respond. If we have more lively discussion than time permits, we will have to cut things off at the top of the hour, and we'll always have a way that you can reach out to Kevin to continue the discussion through other means afterwards. So that'll be the course of the next hour, and I'll just introduce Kevin here before he gets in. So he Kevin Libuit is a public health scientist, and he has spent his career addressing the challenges of integrating DNA sequencing and bioinformatics technologies to strengthen public health decision-making. He has advocated for collaborative open source development over quite a while, certainly all the time that I've had the pleasure of working with him. In the United States, he helped to co-found the US's StaPH-B consortium, the State Public Health Bioinformatics Consortium, and has become quite a key figure just in the bioinformatics community here. And he currently serves in Phage as the vice chair of the Bioinformatics and Pipelines Working Group. And so he works in his day job as Chief Technology Officer in Theiagen Genomics. His role is to advance bioinformatics integration for their public health partners, and their work has led to the adoption of Theiagen's open source solutions and pipelines by over 40 US state and local public health labs and plenty of other labs across the world. So I'll let him speak a little bit more about those things and introduce his own title and a topic up top. So thank you, Kevin. I'll turn off my video and hand it off to you.
All right. Thank you, Danny. And thanks to everyone who's calling in to participate and take the time out of your day to hear me talk about a couple of things that we're doing here at Theiagen Genomics with respect to public health bioinformatics. And also thanks to Jamie Southgate and also all of Phage for allowing me to speak during this session. So like Danny said, I'm Kevin Libuit, Chief Technology Officer at Theiagen Genomics. And yeah, I guess I can kind of hop into it here, get my slides going to kind of organize myself. All right, so hopefully you can see my slides here. And, you know, as I was putting this talk together, or actually when I was first asked to give this talk, first things that came to mind are, you know, this model for distributed public health bioinformatics. And I put the first title there of Containerized Workflows, Cloud Compute Infrastructure, and GUI web application. Afterwards, I'm realizing how much kind of technical jargon is in that, and realizing that, you know, we have really a broad audience here. So hopefully throughout this talk, I can give a perspective of what these terms mean and how they're applied in public health bioinformatics, and really the value that they bring to creating a model that's allowed us to reach so many different laboratories and provide them access to these really critical technologies for pathogen genomics. And the way I'm going to kind of structure my talk is really focusing on the concept or idea of, you know, integration of bioinformatics technologies for public health applications. And, you know, you're seeing bioinformatics now being applied in a number of different public health areas or initiatives. But, you know, my focus today is going to be on pathogen genomics. There's a lot of really similar stories happening, I think, maybe in newborn screening. But the focus of my talk and the perspective I'm giving is with respect to pathogen genomics. And so, again, looking at that development of a model for bioinformatics distribution, I'm giving it from my perspective as a public health bioinformatics scientist. And so there's a couple of caveats on there that this is really my perspective of how things have gone throughout my career over the past 6 years, specifically as a US-based public health bioinformatics scientist. But I think over the years in the different positions I've had really a unique perspective in that I've gotten kind of a front row seat in this journey of developing systems that allow public health laboratories to access these critical technologies. So and right now, I think is an interesting point, kind of a snapshot in where we are because of how critical it has been for laboratories to adopt these technologies, and then all the different kind of systems we've been putting in play over the past 5 years coming to a critical point of fruition where laboratories can really take advantage of what we've been working on for the past, you know, half decade. So kind of breaking this up into three main parts here of, you know, where we are right now, what is this model I'm talking about in terms of containerized workflows, cloud compute infrastructure, and then these GUI web applications. And then I think it's also going to be important to look at how we got here. What were the directives? What were the different key points along the way that allowed us to kind of create this model that's been so effective for public health laboratories? And then also end, you know, in conversation of where to go next. How do we take this to the next level? How do we further refine and optimize the solutions that we've come to with respect to distributing public health resources? So in terms of where we are right now, I think in terms of identifying and creating a model for distributing public health resources or bioinformatics resources are really centered around these three concepts, in that we have these containerized workflows, again, these cloud compute infrastructure, and then these GUI web applications. Again, in each of these three items, I'll dive into a little bit deeper and hopefully elucidate some of the technical components of what I mean to say when I'm talking about containerized workflows, why cloud compute infrastructure has really been one of the best, or at least one of the best models to integrate these technologies, and then why GUI web applications has really kind of expedited the adoption of these technologies for public health scientists. And so in this model, I'm going to be talking about a lot of our use of the Terra web application. So using GUI web applications, containerized workflows, and cloud compute infrastructure is not something that's specific to Terra, but in my perspective, in the work that we've done, it's the model that most closely aligns with the current public health needs with laboratories and fits that specific niche, at least right now. And so in this model, what we've done at Theiagen Genomics is really lean on these core concepts of containerized workflows, cloud compute infrastructure, and GUI web applications to distribute these bioinformatics resources to public health laboratories. As Danny said, you know, right now we're working in over 40 different public health laboratories domestically in the US, but then also through work with APHL and their efforts to bring up these capabilities internationally, we've gotten a chance to really apply this same exact model to laboratories across Western Africa and Southeast Asia. So just kind of showing a quick map of the different laboratories we're able to support right now, spanning different kinds of compute infrastructure, different kinds of laboratory capabilities. This model has really kind of been the through line in being able to rapidly deploy bioinformatics capabilities to laboratories who are starting to generate these critical data and need to be able to analyze these things in a timely manner. So again, this is kind of where we are right now, but to gain context and I think an appreciation of these different resources, I want to kind of give a perspective of how we got here, and at least a perspective of my career over the past 5 years. So when I came into public health, I think that was around 2016, coming out of my master's program at James Madison University, I was transitioning into the US public health system, again, at a really pivotal time. Around 2015, I think, was when the transformation of US public health laboratories began, and that, this was especially for the enteric pathogens and the PulseNet program in the US, where you saw the transition starting from molecular assays like pulse field gel electrophoresis for pathogen surveillance, and then starting to adopt whole genome sequencing and bioinformatics. And it was a really rapid transformation, or at least, in the context of the time, we thought 5 years was pretty rapid, but I think, through the pandemic, we've seen even more rapid transformations happening across the world. But at that time, and I think in around, less than 5 year time span, I kind of watched every US state public health laboratory get equipped with a next-gen sequencing platform. So this was a completely transformative technology for a lot of laboratories that they had to adapt to be able to make value out of it. So within this really short time frame, public health laboratories were given this capability to generate these mass amounts of data that they have not yet analyzed in the past. So at that point, laboratories they could generate these data, but the analysis was really more centralized in that there was the reliance on federal partners, or even to some extent regional partners, to be able to perform the bioinformatics analysis itself. So that road to developing in-house analytical capabilities was quite a long and windy road. Again, something that I got to experience firsthand in my position there at the Virginia State Laboratory. In Virginia, I was one of very few bioinformatics scientists at the state level, and we were really tasked with trying to figure out how do we integrate these technologies, how do we distribute these capabilities across different local and state laboratories. And as we were really focusing on this problem, I think it came to front that there's really three kind of categories of challenges in terms of integrating these technologies. And the way I really saw it, or in the way it was described also in the conversations we were having amongst each other, is that there was the challenge of technical development. So how do we actually write the bioinformatics software that is appropriately analyzing and accurately analyzing the data that was being generated? On top of that, too, was this conversation of compute infrastructure. As I mentioned, this was a transformative technology for a lot of public health laboratories, in that to analyze it, it really requires certain compute infrastructure for really sophisticated informatics and being able to process this volume of data routinely and at a high level, and required compute resources that most public health laboratories did not have available to them. And then the third major challenge, kind of topping or on top of all of that, was the workforce development component. So not only training laboratorians about just bioinformatics in general, or even on how to do the technical development, but even just the translation of the language from how this relates, how these technologies relate to things like PFGE or other technology or other molecular assays that most laboratories were used to. So there was a whole workforce development component that was equally as challenging as the technical component, as the compute infrastructure component. And so, as laboratories had these technologies, they were generating these data, every lab was really facing these different challenges head on. So what became really useful, at least again on the US side of things, were for states to really communicate with one another in terms of how are you addressing the technical development. How did your laboratory, for those that were able to successfully set up a compute infrastructure in their laboratory, to communicate with the other laboratories about how they were able to solve these problems? And then workforce development, we kind of approach in exactly the same way. What were the effective means of communicating the value of these technologies, and also to educate on the approaches and to be able to infer and analyze these data appropriately and reproducibly. And so this kind of gets to what Danny mentioned in my bio there, of creating really communities of open communication. So this is where I think around 2015, 2016 is when we started this US State Public Health Bioinformatics Working Group, StaPH-B, where the first public health practitioners in the US at the state and local levels started communicating with one another, with the federal partners, about how are these problems solved at the federal laboratories, and how can we then solve these same problems at the state and local levels. And then we started kind of coming to best practices for each of these categories of challenges. When we looked at technical development specifically, we were looking at what we wanted as a solution. I think is guidance we got from the CDC and FDA in terms of where they saw laboratories should be at least aiming towards, and then as states and local practitioners, and even with the federal practitioners, we can come with solutions that kind of get us closer to that goal. And so on the technical development side, the goal was to have open source and accessible, interoperable, and reproducible bioinformatics solutions. And I know that that sounds obvious right now, that was the goal, but when we were kind of boots on the ground, a lot of us coming from academic institutions where we didn't necessarily have to share all of our code. We definitely didn't need to be interoperable against different academic institutions or compute infrastructure. And even the conversations of reproducibility, again, at that time, I think a lot of us were coming from an academic institution. Of course, reproducibility is large there, but you were essentially the only one reproducing your own bioinformatics works. So to have it reproducible across multiple scientists, across multiple laboratories, and then the level of quality control that is required for a public health institution just is much higher than what most of us were used to in terms of bioinformatics development at an academic institution. So as we approach these problems, we're all coming with different perspectives in terms of how do we make things accessible, interoperable, and reproducible. And again, we kind of casted a wide net in terms of trying to find the best practices of meeting this goal in terms of technical development. But I think, over the past 2 or 3 years, there have been solidified best practices, or at least, in my perspective, best practices that have enabled the distribution of bioinformatics capabilities with respect to technical development. And that comes by way of these containerized softwares and these workflow managers. And again, this is maybe a little technical term for a lot of the folks on the call. So I wanted to kind of give a parallel maybe when I talk about containerized software in like analogous maybe to something that you might see on the wet bench side of things. Like if you were trying to perform a wet lab assay, something like a DNA extraction or something like that, you can kind of read a protocol, you can see all the steps laid out, and you can see maybe the reagents required to carry out that wet lab protocol. And you can go out and get each one of those individual reagents yourself to carry out that DNA extraction, for example. That's one way to do it. You would be, grabbing all of the reagents that your assay is dependent on. Another way to do it, though, is, in probably a more reproducible way, is to maybe just buy a kit that contains all of those reagents. You get a DNA extraction kit that organizes, packages, or containerizes all of those reagents in a single entity there that you know that if you buy that kit, you have everything you need to perform that assay. And so that's really kind of the same perspective we're taking when we're looking at the dry lab component of things, where we containerize software. So this really increases decreases the barrier to access and interoperability and reproducibility of different software, so that whenever we have specific resources that are developed, different software that are developed, similar to an assay requiring different reagents, software requires different other software dependencies. And that can be a real technical challenge to maintain, install, and even access and interact with. So what we saw as a best practice that is being more and more adopted even in the academic space and even outside of bioinformatics, this concept of containerized software helps to alleviate these challenges of installing and maintenance across different institutions. So that, if I containerize a bioinformatics solution for my laboratory and make it available, I know that Danny can take that same resource and run it in exactly the same way in his laboratory because that software is now containerized. And then the other major concept or really adoption of a practice in public health bioinformatics that we've seen is the use of workflow managers. And again, I was trying to draw the wet lab analogy there. And then maybe I think with workflow managers, you might be, more akin to like a liquid handler or something like that, in that, you want to optimize your process of completing each step in the assay from step 1 to step 10. And you can do that in a number of different ways and try to optimize how you pipette things and all this. But really the best way to scale it and have it reproducible in ways that you can really ensure its quality is maybe getting a liquid handler that you can program and customize and know every step is being taken place in exactly the way you intended to do so. And so again, that's kind of a similar practice that we've seen happen in the dry lab space, in that we were all kind of creating these pipelines that had all these different analytical modules strung together. So it's like process A, B, and C. So for example, in SARS-CoV-2, you might have the assembly step, from the raw read data, create the assembly. Then the next step would be, the lineage assignment. And then the next step might be the clade assignment. So you have these 3 analytical modules. What a pipeline is just merging all those modules together. And 2017 or so, we all had our own different methods of how we wanted to string software together. I think one of the kind of notorious lines you might see in a presentation or even a post or even publications that I've even put out there is, custom scripts for the bioinformatics pipeline, which is almost a euphemism for something that will not be interoperable, will not be reproducible outside of my use there. So rather than these custom scripts and ad hoc solutions for creating these pipelines, there was this adoption of proper languages that were and engines that were developed for this exact task. So we were like, starting to adopt the liquid handler to have a standardized way where we could develop pipelines and also be able to read each other's pipelines and make that human readable and accessible for contribution and collaboration throughout the different public health practitioners there. So, again, in the technical side of things, a lot of the route to accessibility, interoperability, and reproducibility for bioinformatics solutions came by way of containerized software. Again, packaging these software up in things like Docker or Singularity. In the US being an initiative that was really pioneered by Kelsey Florick from Wisconsin State Laboratory and Curtis Kapsack, who's on our team, Theiagen Genomics, in the StaPH-B Docker build. So these are containerized resources of really the most prominent public health bioinformatics resources available. And that's something that, I'm obviously, these are people I work with and I'm very proud of their work. So I'll always tout the success of these projects, but it's also something that is, publicly audited. You can see the number of polls or the number of downloads these resources have. There are multiple resources that have over 1 million polls throughout the public health community. So this isn't just my opinion. These are explicitly valuable, well-utilized resources that have come out of this adoption of this best practice. And then in terms of workflow managers, again, you're seeing the resources that are most widely distributed are no longer these custom scripts and ad hoc solutions of creating these pipelines. Rather, they are pipelines that are built off these workflow managers. So things you might see like SnakeMake, for example, or Nextflow or Whittle, the workflow description language that we write in. These are really best practice systems to have these scalable, accessible technical solutions here. So this was something over the past couple of years, we've really found these best practices kind of solidify with respect to the technical development component. And then when we look at the compute infrastructure, again, this was in 2015, 2016, even still today, you see a number of different methodologies in terms of trying to identify how do we access compute resources that can sustain these bioinformatics analysis. Again, this is a type of analysis that most public health, actually, I don't know of any really public health laboratory that had the equipment that was ready for this transformation of, or transition, I should say, into next-gen sequencing in bioinformatics. From really the simple things of having the appropriate operating system. As I think a lot of the folks on this call at this point realize, a lot of the bioinformatics development happens or occurs within, open source operating systems that are, Unix-based or Linux-based systems, whereas, most government institutions use Windows. So being able to even just run the software was a major challenge. And then on top of that, having the actual compute power, so the CPUs or the memory, and even just the disk space to host and analyze these data, again, were resources not extant within most public health laboratories. And again, I am giving my perspective and working in the US public health system, but I think, as I start to work more alongside APHL and their international efforts, it's really a similar challenges we're seeing with laboratories all over the world, in that how do we find a path for these laboratories to access compute resources to sustain these works. And again, we've seen a lot of different methodologies for getting to this end goal, all from HPCs to being your own sysadmin to your own in-house server using university resources, also HPC kind of model. But I think the one that I've seen really lend itself most closely to the public health needs is the adoption of cloud compute environments. And it's really for the same reasons we're seeing most industries move into cloud compute infrastructure, in that it's really scalable and secure, meeting the most highest credentials for data security, even being used by departments of defenses around the world, and the scalability being nearly infinite at a fingertip to be able to meet the data volumes that laboratories have in terms of surges in data being generated. And also, this is a really key factor here too. It's really readily deployable. Rather than having to, if you were going to set something up like an in-house server, you have to dedicate some level of real estate there. You have to have hardware brought in, and you might even have to have personnel dedicated to administering and maintaining those in-house resources. Or maybe you work with a university that already has that kind of infrastructure in place. But if you're a laboratory that is starting out for the first time generating these data, and you don't have those types of connections, by adopting a cloud compute infrastructure, this could be very readily deployed. And then in that little parenthetical, the caveat there is, pending IT approval. Of course, this is probably one of the more difficult challenges is, educating government IT in terms of, how this is being utilized in public health. I think it can also often be sort of conflated with other applications of cloud compute infrastructure, but in the public health setting, it's a really specific use case that, doesn't necessarily introduce the same security vulnerabilities that IT personnel are often sort of alerted for or sensitive to in that way. So these are the active conversations we've had with different laboratories, is primarily, speaking with IT, educating them on the use case of public health bioinformatics, on the different security compliances a number of these different platforms have. And then, also starting with the value that it brings, in that this is a new type of data. This is an infrastructure modification is required to make to strengthen your public health decisions there. So, that conversation, we've had more and more successfully we've had more success with laboratories in IT personnel in terms of, the benefit of cloud computing environments for again, to meet this end goal of getting compute resources to support these types of work. So in terms of, those best practices and those major challenges of technical development in cloud compute infrastructure, this is, I think, kind of where I saw a lot of the public health best practices being established, in that in the technical development, it was clear to me that containerized workflows were the best way for routine production level bioinformatics to take place. And then again, in my perspective, if you were going to set a laboratory up with the compute infrastructure, cloud compute, if you had all had that as an available option, that was the clear and obvious choice, in my perspective, for a public health laboratory to adopt. But then also in 2020, though, before I started working with Theiagen Genomics and working with Danny Park and the Broad Institute and looking at the different GUI web applications, a major challenge at this point was the workforce development, because we were at this point where we can develop these technical resources and we can get you access to these compute environments, but everything was at the command line. So whenever I would, open up a training event and start a bioinformatics, introductory bioinformatics course, it was always, the first module was always, what is Linux and what is the command line? How do I access the command line? And, at that time, I thought this was the best way to do it, that, bioinformatics happens at the command line, and we need to train our public health scientists to learn, the command line interface. So I'd go to these trainings with different public health practitioners, and they really would be successful. But I think to a number of different laboratories, presenting them with a black terminal and strict text is an intimidating factor that is compounded with all the different, responsibilities of public health scientists. It's not that, these public health scientists aren't able to learn these technologies. It's just the bandwidth required to learn how to, gain a comfort with the command line interface, and then also the routine practice really just wasn't in the cards. And even I think at our highest capacity of being able to train public health scientists at the command line, we were maybe able to train 10 scientists a year or so, maybe 7 of whom were able to carry that as a routine skill set that they brought to their public health laboratory. And in looking at a public health workforce where you have thousands, tens of thousands of scientists that need to interact with bioinformatics technologies, it really isn't a scalable solution to adopt this technology readily. So this is around the time I was introduced to the Terra.bio resource that really encapsulates both of these concepts of containerized workflows and cloud compute infrastructure. But rather than presenting this wall of text and command line interface, you have this graphic user interface, a GUI web application. So no longer am I required to open my session up, my bioinformatics trainings with what is Linux, what is a command, how do I execute something at the CLI. Rather, I can open the training with a website, and it's a drag and drop menus, click button solution for laboratory. So we're able to sort of abstract all those technical nuances of what is a Linux directory structure and why do we need to maintain it. Rather, I can direct them to the web application and get them access to those containerized workflows and that nearly infinite compute resource through a Google Cloud provider. So this is what really helped, again, in my perspective, over the past maybe 18 months or so, solve or I guess come to a best practice in terms of delivering or distributing the bioinformatics capabilities on the workforce development side of things. With a resource like Terra or any kind of GUI web application, I could now focus my trainings on materials that inform public health decision-making. So, a lot of the bioinformatics training that I used to deliver, there was technical content that was not necessarily geared toward informing public health decision-making. It was more so geared to how do I set up my environment so that, I don't get the error code that I keep running into, or that, I find the typo or the extra comma in my command or something like that. Now, that training is still necessary, but I think it's a small minority of the workforce that needs that really technical level of skill set of workflow development. So with Terra kind of introduced to the equation, we're able to have these focused training sessions where, again, for some practitioners, we do the deep dive, we train them on how to develop, access, and contribute to these containerized workflows. But for the vast majority of public health scientists, we can, again, abstract those technical underpinnings through this web application and focus on what are the pieces of information here that are relevant to the public health decisions you need to make. And going to steal a phrase from Peter. We had a phage meeting actually yesterday, and we were talking about the workforce development and applications of these solutions here. And the phrase that stood out to me was he said that, you know, public health scientists need to do less bioinformatics and more public health. And I thought that was a really succinct way to phrase what I'm trying to convey here, in that we didn't want public health scientists doing bioinformatics. We really want public health scientists using bioinformatics so that they can do public health works. And something like a web application, again, it abstracts all the technical components behind the scenes, but still allows access to these really powerful resources for making sense of their data. And when I talk about the technical underpinnings here, I'm more so talking about the compute infrastructure, the CLI components. In a lot of the trainings we deliver now, when we talk about the technical underpinnings, we're talking about the biological components. You know, how does alignment assembly work, and how does that differ from de novo assembly? What does it mean how does lineage assignment occur whenever I have a SARS-CoV-2 assembly? So these are the technical focus points, rather than, you know, setting up, again, you know, your Linux environment or learning the bash, you know, cheat sheet or anything like that. That is now not a part of most of the trainings we deliver. Okay, so to sort of like wrap that all up, again, where we're at right now, we have what I think is a really effective model, at least the most effective model that I've seen in terms of bioinformatics distribution in capturing these three core ideas of containerized workflows. So these workflows that utilize standard languages, that have you know, sustained libraries and you know, continuously updated guidance and specifications, like, again, workflow description language, Nextflow, SnakeMake, etc. Leaning on these containerized packaged software, similar to, you know, the StaPH-B Docker builds. We're also worth mentioning the biocontainers, more so in the academic space, but, you know, there's still the concept of containerized workflow solutions, having nearly infinite scalable compute resources using cloud providers like Google Cloud, and then, you know, allowing for a more friendly user interface through web applications like Terra.bio. So this is, again, as I mentioned, the sort of solution that I've seen most effective in distributing bioinformatics capabilities. So, and a lot of this came to be in Theiagen Genomics works and my role in the pandemic response, in that, you know, rapid bioinformatics deployment was critical, is still critical. And, you know, as we start to shift our focus in other pathogens of concern, it still is an incredibly critical component, is bioinformatics deployment. So with respect to SARS-CoV-2 and COVID-19, you know, we took this same model of containerized workflows, cloud compute infrastructure, and these GUI web applications. And this is what has allowed us to help support, you know, the different laboratories around both the US and internationally, in that we had this really straightforward playbook, in that we would write the workflow, the WDL workflow, the containerized workflow solution. We would work with a laboratory to get them access to the Google Cloud Platform resources. And then we would have the training and onboarding session with the laboratories where we would walk them through how to utilize and interpret these outputs. And what's really powerful about this model too is that we only have to write the workflow once. So, you know, in the US, we started working with a lot of laboratories, or really only two laboratories in the very beginning, Wyoming Public Health Laboratory and Nevada Public Health Laboratory, who really put that front-end investment of developing these workflows for SARS-CoV-2 analysis, and allowed us to get that feedback and develop what, you know, how to properly analyze SARS-CoV-2 genomes. And then once that was solved, we would work with laboratories and getting them access to Google Cloud to be able to run Terra. And again, this was a problem addressed by a couple of different organizations that we have an opportunity to work with. On the US side, the CDC Office of Advanced Molecular Detection made these cloud resources available to any US public health laboratory that required it. So that problem was solved. And then on the international side, we've had incredible opportunities to work with fantastic public health scientists in Noah Hull, I think technical lead manager, I forget the exact title, sorry about that, Noah, but who's overseeing a lot of the global public health deployment, both on the wet lab side and on the dry lab side. But through APHL, a huge number of laboratories now also have access to Google Cloud resources. So with the WIDL workflows kind of already developed and the access to GCP resources solved for a number of laboratories, this is how we were able to rapidly deploy in that, this is how we're able to sort of demonstrate or highlight this kind of a map, is because with these different public health institutions, we now focus on training, onboarding, and supporting their use of these same WIDL workflows that are being utilized in those laboratories we support in the US, also now accessible and being actively utilized by the laboratories internationally. So it's been really an incredible thing to see in just 18 months. Again, this is something that my entire professional career has been addressing, is how do we have solutions for bioinformatics distribution? And again, through this model, through the COVID-19 at the most critical time, we were able to build on those same concepts that we were developing over the past 5 years to really find a critical solution and distribute this incredibly quickly to laboratories that needed it the most here. And so when we talk about rapid deployment, there's laboratories that, again, pending that IT approval to access Google Cloud, we can get you set up within 90 minutes and start having you analyze your data with respect to SARS-CoV-2. So laboratories that were just sequencing for the first time, being able to generate those assemblies, look at the quality, and then get those lineage and clade assignments immediately was really an incredible thing to see, something I'm really proud to be a part of, and work that is sitting on the shoulders of the entire community in terms of these best practices being deployed all around both the academic and public health space. So now moving forward, I think a lot of laboratories now kind of have the bandwidth to start focusing on other pathogens of concern. Well, actually, before I say that, there's still a lot of laboratories that need these capabilities that we are still working with. We're working especially alongside APHL to bring this to other countries that have the sequencing capabilities now that need the dry lab capabilities. So more and more laboratories, we've kind of refined our training and onboarding session where, just last week we finished an incredible training event. I think 20 countries across the African continent were represented, all of whom were given access to Terra Workspaces. And then by the end of it, all of whom were able to perform both genomic characterization and genomic epidemiology of their SARS-CoV-2 data. So that's something that we've been working along APHL, WHO, and CDC to develop that training delivery, and then also kind of get that going on to the different resources. That time, Danny, I saw you turn your camera on. I can kind of
you can wrap up.
Quickly.
Take a minute.
Okay. All right. So moving forward there. Yeah. So now there's kind of a shifting focus to other pathogens of concern on our side in the laboratories we work with most closely. This is kind of coming to highlight in terms of enterics, healthcare associated infections, and antimicrobial resistance pathogens. And really, we're taking that same model in that, we can write the WIDL workflows. We're starting to write those WIDL workflows for a lot of these pathogens. We have written those WIDL workflows. We're continuously advocating for the adoption of cloud compute resources. And then we're starting to onboard and train laboratories. And it's been really an effective model for, again, now shifting the focus to other pathogens of concern and having an opportunity to work with, the federal laboratories. I think a really cool collaboration that's come in the past couple of weeks is working with the Microsnip branch at the CDC and their Microsnip workflow that they've made available and that was being actively utilized for outbreak investigations at the CDC, working alongside them to containerize also that entirety of that Nextflow script there and make that accessible to more laboratories through a GUI web application. And then also on top of this too, it's not only continuing to apply this model, but also to continue to refine this model. There's also, we've kind of pushed this, I think like all bioinformatics scientists, when you're given a really useful resource, you push it to the absolute limit and see where the breakpoints and shortcomings are. And that's like what we're able to do now with the Terra platform, but in a kind of really fortunate position in that we are working alongside the Bro developers on, providing that feedback for the public health laboratories on how to make this a more useful resource for the public health community. And of course, there's also shortcomings here in that, this model of containerized workflows, cloud compute infrastructure, and GUI web applications. I focused on using WIDL, Docker, Google Cloud, and Terra because that's the system that we've been kind of leaning on. But not every laboratory will be able to adopt Terra as their GUI web application because they may not have access to Google Cloud. You might have in-house solutions that are, not explicitly compatible to Whittle workflow. So there is an understanding of this is an incredibly effective solution, but of course there are shortcomings. We are aware of its limits, and that's kind of where we're at in terms of working with the Broad and other developers to address those head on. So with that, I just have quick acknowledgements and discussions. So big acknowledgement to the Theiagen Genomics team. I think most of whom are on here. So let me just kind of see if, so Joel Savinsky, obviously the CEO of Theiagen Genomics, who really started on this path, working first with Danny Park and getting an awareness of Terra.bio and its applications in public health. And then also, I think I mentioned Curtis Capsack, other people on our team here, Robert Petit and Emily Smith, Frank Ambrosio being the bioinformatics scientist, really bringing these solutions at the forefront. And then our newest member, Sage, also on the bioinformatics side. And then also the huge help from the APHL. I mentioned Noah Hall and his advocacy for these different solutions. And then also the entire Office of Advanced Molecular Detection at the CDC. I think I've mentioned a couple of times, but Greg Armstrong, Duncan McCannell, Scott Salmons, and that entire team who throughout my entire career, more or less, supported me indirectly or directly. So thank you also to the CDC and also all the phage contributors in the whole public health bioinformatics community at large. I think what I hope to convey here is that these solutions are a bringing to fruition the best practices that have been developed across the field. And this is our contribution to continuously progress that. So with that, I will take some questions. Sorry, Danny.
Thank you, Kevin. Well, it takes a village, as you say, right?
Yes.
For folks here, I would encourage you to put any questions you have either in the chat or in the Q&A, and we'll start to field those. Thank you so much, Kevin, for taking us on your journey, or the journey of your perspective of just U.S. public health in this past few years. I'll start us off with just kind of things that come to mind myself as I'm hearing you describe your perspective and kind of the way that you frame your strategy around addressing compute needs for public health. So you kind of talk about this 3-tiered strategy, which is part of your title and your opening slides. And I guess what I'm wondering is, a lot of that has been from lessons learned in the US context and also applied globally kind of more recently. But I to what extent do you think, from what you've seen so far, does any of that strategy look different or change in a global context versus the US as far as you've, to the extent that you've learned so far? Or is some of it like generalizable, or some bits have to shift a bit?
No, that is a great question. Yeah. So in the preface of that was that I had this US perspective of what was happening in the US public health infrastructure. But I think what has been incredibly surprising is how common these are, the same exact challenges, even for international laboratories, and how they can really sort of be, to some extent, categorized in the technical development challenges, the compute access, and then also the workforce development. So it has been a model that we could really apply to laboratories across the world as well. At least as thus far, I'm very still, naive to all the complexities of global public health. But of course, that's the conversations I have with Phage in my participation in that working group, and also alongside Noah Hall and APHL. It seems that these challenges are not specific to the US system, more so that public health laboratories adopting these new technologies that really need to transform their infrastructure to support bioinformatics run into these same challenges. So it's been a model that has found a through line in that.
Okay, and we're, I have more questions, but we're starting to get a few questions in the Q&A starting to come in. And I think one that I'll highlight from Frank here is it'd be informative to talk a little bit about data ownership, particularly with regards to cloud platforms.
Oh, that's a great question. And I don't know that I'll be able to speak incredibly in depth about that, but in terms of data ownership, whenever there's an adoption of the cloud compute resource, it's not a giving over of data ownership to whomever the Google Cloud or the cloud provider is. So it's not like it becomes Google's data or AWS's data, or even in this case, or AWS's data. So my understanding, and I have a pretty naive perspective on this. So Dan, if you have more perspective on this, please feel free to jump in. But the data ownership is still, maintained by the laboratory that is generating it. And those conversations of data security, data ownership, and being able to host your data on the cloud platforms, need to be taken into account. But if you're using a Google Cloud resource, it doesn't become Google's data in any sense. It's still your data. It's your use of their resources to host your data.
Yeah, I mean, from my knowledge, which is more specific to the systems I work with, I think it does really vary a lot per system. Like, depending on what cloud platform you're using. I'm not talking about like whether it's Google or Amazon, but whether you use a like a software as a service kind of platform all baked in or something like that. So it's certainly one of the things to pay the closest attention to as you start to kick around these types of solutions. There's also a question here about the business model for this work, and I'm not exactly sure whether that's talking about the analytics itself for the public health end user, like how they fund that type of work versus what sustains entities like yourself
Sure.
that actually provide a lot of the glue bits in this.
Yeah, these are great questions. Thank you, Frank, for submitting these. So I guess we could talk about that in a couple different contexts. So for the Terra resource, that is a Broad hosted platform alongside Verily Life Sciences and I think Microsoft. So there's a number of funding sources that make that freely available. So whenever you use Terra, it's a free and open resource. What the user pays for is just their compute resources. So like the data storage and the compute to actually process and analyze these data. In terms of the business model for Theiagen Genomics, we work alongside public health laboratories to create and write these open source resources. So I mentioned that in the SARS-CoV-2 we work with primarily Wyoming Public Health Laboratory and Nevada Public Health Laboratory to make these little workflows. But our sort of ethos on this is that these are public health laboratories that are paying for the development of public health resources. So as soon as those are created, we make those explicitly open source and accessible to the public health community at large. So there are a number of laboratories who set up their own Terra environments and use those same workflows without ever even really interacting with us. So those are open and freely available to the public health community. So Frank, hopefully in terms of the business model, we get funded to work alongside public health scientists to do these works, to kind of carry out these initiatives. And we offer, I guess, just the experience and perspective of being practitioners in the field. And then we make these available, and then we help to train and onboard laboratories that actually use these.
And certainly for those who want to continue to follow on with questions or clarifications, we can reach out to Kevin over email, or Slack is a great way to reach him in whatever workspace you might, whether it's Phage or Microbioinfo or something like that. Kevin, I kind of had a question as well, which was, there was a point towards the end there which made me wonder kind of more broadly whether there's a inherent tension in any kind of solution between addressing the needs of pipeline users versus pipeline authors. And it's one of these things where, traditionally a lot of informatics solutions for public health erred on the side of standardization and increasing access. But you didn't really get to write your own pipeline. You had to use the one that was provided by a company or by whoever, right, that kind of thing. So it errs on the side of standardization, increasing access to kind of bench users, versus, in the past few years, there's been a lot of empowerment really to be able to participate in the methods development and the development of one's own pipeline. Are these two needs in conflict when you how, I guess this is kind of a question of mine that I feel like it impacts how people choose how to solve some of these questions.
Wait, so sorry, do you mind rephrasing that? So like the conflict of the folks who are developing these versus the folks who may be using these?
I'll put it this way. You kind of at one point said that you felt that public health labs should be doing less bioinformatics, right? And should be doing more public health, right? And there's ways that computational tools with all the infrastructure and all the pipelines stuff can be really geared towards, here, do the public health. We've solved the informatics for you, versus here, let me give you the keys to doing the authoring yourself. A lot of early 2020 wouldn't have gotten off the ground if people hadn't actually made their own pipelines to handle, you know what I mean? Is there,
Yeah.
can you have both? Or is it always one?
I think the tension is probably necessary and required, right? It's almost like it keeps the scientific rigor in that. I think there will always be a technical community who will be writing their own workflows. And I think that, and that's kind of how I framed our workforce directives now. Like for some, we need there to be a community of technical practitioners who can read the code, assess it, and be able to analyze and review each other's source code. But that is not the majority of public health scientists. As I mentioned, I think, most public health scientists have a whole swath of responsibilities on top of the bioinformatics analysis that they need to do as well, in terms of is maintaining the volume in wet lab assays, being compliant, ensuring they have the validated systems, and then they need to integrate bioinformatics into that. So in the context of, less bioinformatics, more public health, it's having a developer community that can review each other, have open source, and contribute to each other's source code, and also have that important review. But then for most scientists, be able to present it to them in a way that they're not doing bioinformatics, they're using bioinformatics. And again, maybe there's semantic there that may be disagreeable, but I like that framework of public health scientists doing public health and utilizing a bioinformatics resource. But nonetheless, the absolute importance of the technical communities that have an awareness. And that's also something we try to advocate for and build up in terms of educational materials on how to utilize, or write these workflows and utilize these systems.
Okay, last one here, which I think is just a quickie, which is simply as you described a lot of the specific solutions that you've adopted around Terra and things like that. Are there mock data sets or practice kind of workspaces that people can get started with and things like that? And keep it quick, we'll wrap up after this.
Yeah, I think there are a couple of different mock workspaces. Actually, Danny, you might know more about that than I do in terms of what the Broad makes available, but I think a lot of Danny's workflows from the viral pipes are in public accessible mock workspaces with dummy data. And so I can try to find a link to that, but
yeah, I know of some of our own stuff, but I think your stuff is a little more widely adopted. So I think part of it is just like the how do you kind of start to play type thing, and maybe that's kind of a hook for a future conversation.
Yeah, certainly. Again, if you're interested in using these resources, feel free to contact us. I can put my email in the chat for folks if they want to contact me, but I would direct that individual to the Terra.bio website itself, where there are a couple of different demo workspaces. But again, you can also email me directly if you have interest in starting to utilize these. And we do have a couple of different, training videos and things like that out there available for how Terra is actually utilized in public health settings.
All right. Well, with that, I think we're hitting the end of our hour. And so, Kevin, I wanted to thank you very much for taking us on this tour, giving your perspective, and answering a lot of questions. And thanks to everyone here who's taken the hour out of your day to come listen and participate in the lively discussion. So thank you so much. I believe at some point in the coming days, the recording will be all packaged up and distributed through other channels for those who were not able to make this live. So thank you all, and have a good evening or morning wherever you are.
Thanks all, appreciate it. Thanks, Danny.
Thank you, everyone.